Hi everyone, I am Takumi, machine learning engineer at Google Advanced Solutions Lab. Currently, a lot of people are talking about generative AI and its new advancement. And as some of you may know, Google and Google Cloud also release so many generative AI related new products and features. But in this video series, our goal is not to create a state-of-art generative AIs, nor to introduce Google Cloud new products. Instead, we will explain what kind of technology is working behind them. And especially in this video, I'm going to talk about how to actually create a very simple generative model, image captioning model, by using technologies like encoder-decoder, attention mechanism, and a bit transformer. If you're not very familiar with these concepts, I recommend checking other videos talking about them before this. Okay, so if you're ready, let's talk about image captioning tasks and dataset at first. We're gonna use this kind of dataset. As you can see, there are a lot of pairs of images and text data. And our goal is to build and train a model that can generate these kind of text captions based on images. And we'll make it happen by building this kind of model. As you can see, it is kind of encoder-decoder model. But in this case, encoder and decoder handle different modality of data, which is image and text. So we pass images to encoder at first, and it extracts information from the images and creates some feature vectors. And then the vectors are passed to the decoder, which actually build captions by generating words one by one. So this encoder part is easy. You can use any kinds of image backbone like ResNet, EfficientNet, or Vision Transformer. What we want to do here is to extract features by using that kind of backbones. So code is very simple too. In terms of the code, we're going to see the entire notebook example in the next video. So here, let's just focus on some important lines. As you can see, we are using classical Inception ResNet v2 here from Keras applications. But again, this can be any image backbones. So the next part, the decoder, is a bit complex. So let's take a look very carefully. So this is the entire architecture of the decoder. It gets words one by one and mix the information of words and images, which is coming from the encoder output, and try to predict the next words. So this decoder itself is a kind of iterative operation. So by calling it again and again autoregressively, we can eventually generate text captions. There are so many variations for this decoder design, but here we build transformer-like architecture, although we still use RNN or GRU. So let's zoom into each component. The first embedding layer creates word embeddings, which was discussed in other videos. And we are passing it to GRU layer. If you forgot what GRU is, it's a variation of recurrent neural network, or you can call RNN. RNN takes inputs and updates its internal states and generate output. So by passing sequential data like text data, it keeps the sequential dependencies from previous inputs like previous words. The GRU output goes to attention layer, which mixes the information of text and image. In TensorFlow Keras, we can use predefined layers in the same way as other layers. There are multiple implementations, but here we simply use TF Keras layers attention. But if you want to use more transformer-like architecture, you can also pick up TF Keras layers multi-head attention, which uses multiple attention heads. You can simply switch and use it in almost the same way. Inside attention layer, it looks like this. as you may have already seen in another video about attention mechanism. But unique thing here is it pays attention to image feature from text data. By doing so, it can calculate the attention score by mixing both information. Going back to code, you can see this attention layer takes two inputs, GRU output and encoder output. Internally, GRU output is used as attention query and key, and encoder output as value. The last components are add layer and layer normalization layer. Add layer just adds two same-shaped vectors. As you can see here, GRU output is passed to attention layer as we discussed, and to this add layer directly. These two flows are eventually merged in this add layer. This kind of architecture is called skip connection, which has been a very popular deep neural network design pattern since ResNet. So it is also called residual connection. This skip connection is very useful, especially when you want to design a very deep neural network. And it is also used in the transformer. With this, now we could build entire decoder. So we are ready to train the encoder-decoder image captioning model using the captioning dataset. We will see how it works in the next video. But before moving on to the next one, I want to explain a bit more about inference phase, where we can actually generate captions for arbitrary images, because this process may look a bit complex. Here you can see 3 steps, and we're going to implement these steps in a custom inference function. The number 1, generate a GRU initial state and create a start token. In training phase, TensorFlow Keras can automatically handle GRU state for each sequence. But in this inference phase, since we design our own custom function, we need to write a logic to deal with it explicitly. So at the beginning of each captioning, we explicitly initialize the GRU state with some value. And at the same time, remember our decoder is an autoregressive function, but since we haven't get any word prediction yet at the beginning of the inference, we pass start token, which is a special token that means the beginning of the sentence. Number 2, pass an input image to the encoder and extract the feature vector as we discussed. And number 3, pass the vector to this time decoder and generate a caption word in the for loop until it returns end token or it reaches to max caption length, which is just a hyperparameter specifying some number like the 64. And in this for loop, we define all the procedures of caption generation by calling the decoder autoregressively. End token is a special token too, which means the end of the sequence. So when our decoder generates this token, we can finish this for loop. Or you can go out of the loop when the length of the caption reaches some number, max caption length. Let's take a look at the code one by one. In the first step, we initialize two things, GRU state and start token. In this case, GRU state is simply initialized with 0 vectors, and we set start tokens as the first input word for the decoder. In terms of the word to index function used here, I'm going to explain in the next video. But basically, it just tokenized the words to word token, which is the standard text preprocessing technique. In the next step, we preprocess the input image a bit and pass it to the encoder we train. In terms of the image preprocessing, it reads and decodes JPEG in the first line, and it resizes it from any arbitrary resolutions to specific resolution. And it changes the scale from 0 to 255 to 0 to 1 in the third line. And the last phase, decoder for loop. It is a bit complex, so I will explain in the next video more in detail with the actual code. But the main thing here is to call the decoder by passing three things. Deck input means decoder input, which should have a word token predicted in the previous iteration. And as we talked, if it is the first iteration, this would be the start token. GRU state is the current GRU state we discussed. And please note that the decoder also output the updated GRU state. And last but not least, features. This is the image feature we extracted with the encoder. By passing them, we can get the actual next word prediction. This is a very simple text generation model from images, but this kind of iteration is very similar even in very large language generation models like Google Bard. They basically predict the next word autoregressively in this way, one by one, based on some information, and learned knowledge, which is embedded in a huge number of parameters. In the next video, I will walk you through the entire notebook, and then we will check what kind of captions this model can generate. Thank you so much for watching, and see you in the next video.